Hi. So we finished up section 5.1, and I have 5.1, some extra practice problems, just to help some of these concepts sink in a little more, do a few more examples. So question 1 deals with a winch that's on a sailboat, and we know it's 8 inches in diameter. We're using that to pull in these sheets, which are ropes used to control the corners of the sail. And then to the nearest degree, we're trying to figure out how far should the winch be turned to pull in 2 feet of rope, right? So if you look at my completed notes that I have posted on Canvas, I actually did this problem using degrees. I think maybe it's a little more work to do using degrees. So I thought it would be worthwhile here. I'm going to show you how you can easily do this using radians. Right, so remember, when we're thinking about radians, we can define theta to be equal to the arc length s divided by the radius. Right, so we're trying to figure out the angle we need to pull it in, right? So maybe we can think about this in terms of radians and then convert the radians into degrees, right, is my thought process. So the arc length that we would have here would be the 2 feet, right? Because that's what we're trying to pull in on the rope, right? Because if you have a winch here, right, and if the rope's touching this, and when you turn this, the rope that comes in would be kind of like an arc length, right? Because if you turn it from here to here, let me use a different color. So if this is a starting point, maybe, and this is my ending point after turning the winch, right, then this S part would be the arc length, which would describe how much of the rope you were pulled in, right? The distance going from A to A prime, right, would be the arc length. So then we need to divide this by the radius. So the diameter is 8 inches, right, which means the radius would be 4 inches. Right, so we'd have 4 inches. Right, so I'm taking 2 feet divided by 4 inches. So I need to have the same unit in the top and bottom, right? So what I can do is replace 2 feet with 24 inches. Right, and then divide that by 4 inches, which the inches cancel out, and we're left with just 6. Right, so we're unitless, so there's 6 radians. Right, so then we want our answer to be to the nearest degree, right? So I need to figure out, well, how many degrees is in 6 radians, right? So this would be equal to 6 times 180 degrees over pi, which turns out to be approximately equal to 344 degrees, right? So if we take 6 times 180 divided by pi, round the nearest degree, you'll get 344, right? And just to point something out, if you haven't seen this used before, for approximately, you can use like a wavy equal sign or an equal sign with a dot above it, right? They both mean approximately equal to, right? All right, so we have just 2 more problems, but the next 2 problems have multiple parts to them. So number 2, we're told that a truck has a 2.5 foot tire in diameter, and that's the diameter measurement. So part A says, what distance will the truck travel with 1 rotation of the wheels? Give the exact distance and an approximation of the nearest tenth of a foot, right? So it's going to, 1 rotation, it's going to go a distance of 1 circumference, right? So circumference is equal to pi times diameter, right? So this would be equal to pi times 2.5 feet. Oops. Which is equal to 2.5 feet. So this would be the exact, right? And then to get the approximate, 2.5 pi feet, sorry. And then to get the approximate, we would just take 2.5 times pi. To the nearest tenth would be 7.9 feet. Right, so this is the approximate. Right. And again, I'm not doing all these calculations on my calculator, right? But you should be able to do this okay. So I can just take 2.5 times pi, and we want to round that to the nearest tenth, so 1 decimal spot, right? So we look to the right to the 8, and that rounds it up, so we get 7.9, right? And then part B says, well, how far will the truck travel with 10,000 rotations of the same wheels? Give the exact distance and approximation to the nearest foot, right? So the exact, right, would be 10,000 times the 2.5 pi feet, right, which would be equal to 25,000 pi feet. Right, that's the exact. And then the approximate would be approximately equal to 78,540 feet. Right, so again, you could just take 25,000 times pi on your calculator and get that approximation, round to the nearest foot. Right. So then part C says if the wheel turns at 672 rotations per minute, RPM, what is the angular speed? Right, so RPM equals rotation per minute. Right, so remember, for angular speed, we have omega equals sigma divided by t, right? Or excuse me, that's theta. So what we need to do, right, is figure out what theta would be. So theta is going to be that angle, and we're going 672 rotations. So in other words, theta is going to be equal to 672 times 2 pi, right, if that makes sense. Because we're going 2 pi radians 672 times, right? That's what that means when we have 672 rotations. And then t, the time, would be 1 minute, right? Because we're doing 672 rotations in 1 minute. And this would be, this would be in radians per 1 minute. So then, simplifying this becomes 1,344 pi per minute, right? So that's the angular speed, right? Remember, angular speed should always have like degrees per minute, radians per minute, should be your units, right? Where linear speed is like feet per minute, like some distance per minute, right? So then part D says if the wheels turn at 672 rotations per minute, what is the linear speed in feet per minute? Give the exact distance and an approximation to the nearest whole unit, right? So, to fill this in, we have V equals S divided by T, right? Which, remember, S is equal to R theta divided by T. So we can just fill these things in. Whoops, let me fix this R. Right, so the radius, the diameter rather, is 2.5 feet, right? So the radius would be equal to 1.25 feet, right? Because it'd be half that. So when we fill this in, the radius is 1.25 feet. And then we need to multiply it by the angle in radians. So that would be times 672 times 2 pi, right? Same logic as before, because we're doing 672 rotations, and each rotation is 2 pi radians, right? And then we need to divide that by t, time, which is 1 minute, right? So if we simplify this, we get this as 1,680 pi feet per minute, per 1 minute. Right, so that's the exact distance, right? We wanted feet per minute. So then the approximation would come from, taking 1,680, multiplying it by pi. That gives me 5,278 feet per minute. Which there's 5,280 feet in a mile, right? So they're going roughly a mile a minute, right? That's pretty quick. Right. So then E says if the wheel turns at 672 RPM, what is the linear speed in miles per hour? Round to the nearest mile per hour. Right. So we already found the linear speed in feet per minute. So that was 1,680 feet per 1 minute. And essentially all we want to do is just convert this into miles per hour, right? So if I want to get rid of feet, I need to put feet here, and I can put mile here. So 1 mile is 5,280 feet. And then, so the feet are gone. Now we're in miles per minute. So I want to turn the minutes into hours. So minutes is on the bottom, so I want to put minutes on the top. So there are 60 minutes in 1 hour. Right, so this cancels the minutes. So you can see what we're left with is miles per hour. Right. So multiplying straight across and simplifying, we would get what? Whoops, this should be pi here. I forgot to write that down. So this should be 1680 pi. So 1,680 pi times 60. And that's in miles. And then divide that by, so we just have 5,280 on the bottom, and the unit on the bottom is hours. So then if I approximate that, that comes out to be 60 miles per hour, right? Rounding to the nearest mile per hour. All right, so we have one more question left. So number 3. It says the minute hand of a clock moves from 12:10 to 12:15. How many degrees does it move during this time, right? So the way I think of this one is, full rotation of a clock is 360 degrees, and there are 60 minutes in one rotation, right? So we're moving 5 minutes. So that's 5 divided by 60 of a rotation, right? 5 minutes out of 60 total minutes. So then if you multiply these, we end up getting 30 degrees, right? So this is the, part of a rotation. Right? So then part B is how many radians does this move during this time? Could do this a couple of ways. We could just take 30 degrees and convert it into radians. Or you could take, basically take this same, this same idea and just replace the 360 with 2 pi, right? Because we're doing with a rotation in radians now. We're still going 5/60th of a rotation. So simplifying this should come out to be pi over 6. Right? And this was actually one of the common degree radian measurements that we should know, that 30 degrees is pi over 6. Right? We'll use that a lot in this class. Right? So then part C says if the minute hand is 9 inches in length, determine the exact distance that the tip of the minute hand travels during the time. Right? So we have a clock here. The minute hand, is on the 10, and it's going to the 15. We're trying to figure out the tip of the hand, how much does that move, right? Well, remember we use to calculate that, we have S equals R theta, right? Trying to figure out the exact distance, so we're using the arc length, right? S equals R theta. So the radius here is 9 inches. Theta would be pi over 6, right? We already figured that out in part B. So multiplying and simplifying, you should get 3 pi over 2 inches. Right. All right. So then part D. So we got 3 parts left for this problem. So same clock, right? Part D says determine the exact angular speed of the minute hand in radians per minute, right? So angular speed, we use, omega equals theta divided by t. So theta is pi over 6 radians. I already calculated that before. And the time that's happening is 5 minutes, right? So simplifying this, you should get pi over 30 radians per minute. Right? So then part E, what's the exact linear speed in inches per minute of the tip of the minute hand? Right? So this time we want the linear speed. So, we have V equals S divided by T, which equals R theta divided by T, right? Because S equals R theta. So just plugging that in. What we get here is 9 inches times pi over 6, right? Because we have pi over 6 radians, and we're doing this in 5 minutes. So time is 5 minutes. So again, simplifying this, you should get... you end up getting 9 pi over 30 inches per minute, which is equal to 3 pi over 10 inches per minute. Right, so we can divide top and bottom by 3. So that's the exact linear speed. And then part F asks about what's the amount of area that the minute hand sweeps out during this time. Give the exact area in terms of pi, and then the approximate to the nearest square inch, right? So a couple of ways to do this, right? So the area of a sector, remember, is equal to, so we need to figure out the portion that we're going for a full rotation. So there's 2 pi radians in the whole circle, and we're just going pi over 6 part of the way, right? And then we need to multiply by the area of the whole circle, which would be pi r squared. So this would be pi times 9 squared square inches, right? So we can simplify this. This would be equivalent to pi over 6 times 1 over 2 pi times pi times 9 squared inches squared, which would be equal to, so these pi's can cancel out, right? So what we end up getting is, let's see, this would be, 1/12 times pi times 81 square inches. So this ends up being 81 pi over 12 square inches, which we can divide top and bottom by 3. So that would be 27 pi over 4 square inches. So there's the exact answer. And then this is approximately equal to 21 square inches, right? All right, so that's all I have for this video. So if you have any questions over section 5.1, make sure you let me know. Thanks.